In this module, we're going to look at acid and base reactions. By the end of this module, you should be able to write a balanced equation representing the reaction between an acid and a base. When we look at acid and base reactions, we also call these neutralization reactions, simply because the acid neutralizes the base neutralizes the acid. Typically, our products end up as a neutral or near neutral solution. In this case, our example is with calcium carbonate and sulfuric acid. This is something that typically happens when we see areas where there are high levels of acid rain. The calcium carbonate made in the statue is actually affected and reacts with some of the sulfuric acid in the rain. And over time, we can start to see damage done to the statue as the calcium carbonate is reacted away and producing calcium sulfate, which may wash away because it's not part of the limestone statue, as well as water and CO2 gas.
Another type of reaction that we see often is an acid-base reaction. And this is actually a reaction that you can do safely at home. We have vinegar, which is a dilute solution of acetic acid, and just baking soda that we often find in household, often used in cooking or in your refrigerator to keep it smelling fresh. And what we have here is a flask where we've got our acetic acid, our vinegar in the flask, and I have our baking soda in the balloon. And we have a little bit of indicator here, the bromocresol green, that will change colors as the pH of the solution becomes more basic. So I'm going to raise our balloon to dump in the baking soda. And we're going to start to see the balloon inflate as we're producing the CO2. So what we have is it's producing the carbon dioxide gas as the reaction occurs, and we can see a slight change in the color of the solution as the solution became more basic.
This just shows us an overview of some common properties associated with acids and bases. For example, bases tend to have a bitter taste and they're slippery, so we can think of something like soaps. We do see color changes in plant dyes. This is how we take advantage of indicators. And we know that aqueous base solutions, like many other electrolyte solutions, will also conduct electricity. When I look at acids, what we know is that they have a sour taste. So if you've ever tasted a lemon and tasted how sour it was, that's from high levels of our citric acid. We can also see color changes in plant dyes as well, because we can see the pH changes associated with those, and that's often used in indicators or in pH paper. We can get the reaction of acids with metals to produce hydrogen gas. And like the example we looked at previously, we see we can get the production of CO2 when the acid reacts with a carbonate or a bicarbonate compound. Many times when we look at acid-base reactions, what we see is that we get an acid and a base react to form a salt and water. However, if there's a bicarbonate or carbonate present, CO2 will always be one of the products, and these are considered to be gas evolution reactions. Just like bases and other electrolytes, aqueous acid solutions are also capable of conducting electricity in water. So we're going to look at two different definitions of acids and bases, and it's not that one definition is completely different than the other. They're both very closely related, and what we see is if something is an Arrhenius acid, it's also going to be a Bronsted-Lowry acid. The reason for the different definitions is because just basically the breadth of the definition. So when we look at an Arrhenius definition, what we know is it's a substance that produces H plus or H3O plus, and we'll talk about that in a minute, in water. So if I look at HCl and water, what I see is that H3O plus ions are produced. Arrhenius base produces OH minus in water. So for example, ammonia, NH3, reacting with water produces NH4 plus and OH minus. The caveat with the Arrhenius acid-base model is that it must be in water. And so this works great for many things that we look at in general chemistry, but there are situations where we have stuff that's not in aqueous solution, that's not in water, but it's still behaving as an acid or a base. And so we need a little bit broader definition to clarify our definition of what we mean by an acid or a base. Now let's talk a little bit about the hydronium ion that we mentioned on the previous slide. When we look at hydrogen, so a neutral hydrogen atom, what we see is that it has one proton and one electron. Well, if I remove an electron so that I'm going to a positively charged ion, then what I'm left with is a single proton. Okay. Now, A couple of things. One, a single proton will be very small. It's not going to be present in aqueous solution, just floating around as a proton. And two, generally we are dealing with an aqueous solution, or we're dealing with something that can be protonated or can accept that proton. And so in this case, we're looking at water. And so what we actually get is H3O plus, because we have 3 hydrogens, an oxygen, and it would be resulting in a plus charge because we have a water molecule that has accepted that H plus ion and forming H3O plus. So anytime we see H3O plus, H plus, proton, hydronium, all of these mean exactly the same thing. And although we write it in many different ways, it all means this, the hydronium ion, the H3O plus. So frequently you'll see H plus written just as a shorthand way of writing that, but we need to remember that that actually does mean H3O plus. So now let's look at a little bit broader definition. This is called the Bronstedacidbase definition, or called the Bronsted-Lowry acid-base definition. And we can still look at similar substances, but what we look at now is what's happening to that proton. So we say a Bronsted acid is a proton donor, a Bronsted base is a proton acceptor. So when we're looking at a reaction, we can determine what substance is acting as an acid and what substance is acting as a base. But we have to do it within the context of the chemical equation. We have to know how it's behaving relative to the other species that are present. So when I look at my reaction here, what I see is I've got a base, in this case it's NH3, plus my acid, which in this case is actually water, but it's behaving as an acid. Notice that we have equilibrium arrows, and all these mean is that the reaction proceeds in both the forward and the reverse direction. So it's not that we consume all of our reactants or produce all of our products, but that we have some of every substance present in our mixture. Then we go to the other side of the equation. This is NH4 plus, and we have OH minus. And so what we look at are our pairs of substances that have changed by a single proton. So we see NH3 here goes to NH4 plus over here. And on the process of going from NH3 to NH4 plus, it has gained a proton. And so if it's a base, it's willing to accept a proton, then the NH3 is our base. Notice that after it accepts the proton, now it has an H plus, now it's willing to donate a proton, so it's acting as an acid. The same argument can be said for our acid and base here, our water to our OH minus. In this case, water goes to OH minus, and in order to do that, it actually has to donate a proton. Now it donated it to the NH3, but what we have left is OH minus. So here, water is actually acting as an acid because it's willing to donate a proton. Over here, OH minus is a base because it's now willing to accept a proton. If it accepts a proton, it will go back to the form of H2O and back to our reactant. Notice a couple of things. One, we have an acid and a base on both sides of the reaction, and we notice that if the NH3 was the base, its partner over here, NH4 plus, is the acid. So if you can figure out one, you can figure out the other species as well. So the most common thing we see in an acid-base reaction or neutralization reaction is that we form a salt and water. And so when we look at a reaction, we say it's forming salt. That doesn't always mean table salt or sodium chloride. A salt has actually a broader definition. There are actually lots and lots of salts. First, it must be an ionic compound, and its cation cannot be H plus, and its anion cannot be OH minus or O2 minus. So any other ionic compound is going to classify as a salt. So beyond table salt for that. And what we know is that salts are all strong electrolytes. Not all of them are soluble, but they're all strong electrolytes. They would all conduct electricity in water. And so if you ever go into a lab, what you'll frequently see is you'll see some baking soda and perhaps some weak acid available, so that if there's an acid or a base spill, we can actually neutralize that acid or base to produce salt and water. So we still have a mess to clean up, but now we have a neutralized mess instead of dealing with, say, a strong acid or a strong base, which is going to be a little bit harder to handle. So let's look at some examples of some neutralization reactions. Here we have HCl, our acid, NaOH, our base, and we form NaCl and water. Now, much like we made the argument for our precipitation reactions where we're kind of swapping anions, we're going to do the same thing here. H is currently paired with the Cl-. The only other anion available for it to pair with is the OH-. So we see the molecule formed there, our water molecule formed from the H and the OH-. And then we get our NaNCl to form our sodium chloride salt. We see the same thing as we go down. We have H and OH and K and Br form our salt and water in the products. Here we have our H and our OH and our NO3 and Ba. Now notice when I get down here that I don't have a subscript for my nitrate in the HNO3, but I do have a subscript in my product because I have to redetermine what the formula is going to be based on what I know about the ions. So for example, barium has a 2+ charge, nitrate has a -1 charge, and so the compound formed from these is BaNO3 2. And that also means that I'm going to have to put some coefficients in order to have a balanced chemical equation. So when we're looking at our potential products, we always have to refine what the subscripts will be for that particular ionic compound. For the first two examples, we didn't have to worry about that too much because we had +1 and -1 for both our cation and anion. But here we have a +2 charge on our cation and a -1 charge on the anion. So what is the net ionic reaction for a neutralization reaction? Here we're given the molecular equation. We have a balanced chemical equation, so we don't have to do anything else to the equation. What we need to do now is we need to write our complete ionic equation. So this is our molecular equation. Now we're going to write our complete ionic equation. And remember that anything that's listed as aqueous is broken apart into its ions. So we have H+, that's going to be aqueous, plus Br- aqueous, plus K+, aqueous, plus OH- aqueous. So now we have all of our reactants taken care of. Both of them are aqueous, so everything is written as an ion. And then we go to our product side, and we see that we have K+ aqueous, and Br aqueous because we have an aqueous substance there. But notice that my water is not aqueous, so I'm going to leave it written as H2O. Anything that is a pure liquid or a solid or something in the gas phase will always be written as is. The only things we can divide are those things that are in the aqueous phase, and we can dissociate those into their component ions, which is how they would actually exist in solution. Now we need to go through and find our spectator ions. So what I want to look for is anything that's exactly the same on both the reactant and product side, both the formula and the state of matter. So now when I look at my equation, what I see is that Br- is the same on both sides. So that will be considered a spectator ion, so I can cancel it out. K+ is exactly the same on both sides, also a spectator ion, so I can cancel it out. Now what I want to do is look at what's left. Notice that I have H+ aqueous plus OH- aqueous going to H2O liquid. So this is the net ionic equation for my neutralization reaction. Note that for many of our acid-base type reactions, this will be our neutralization reaction. So one thing that we do in labs is actually do something called an acid-base titration. And we do this in order to determine the concentration of an unknown solution because we know the concentration and volume of one of our solutions and we know the volume of the other. We'll talk more about this when we look at stoichiometry and look at the calculations associated with a balanced reaction between the amounts of reactants and the amount of products. A couple of things we look at when we're dealing with acid-base titrations are the equivalence point. And what this is it means when the H3O+ and the OH- concentrations are equal to one another. That doesn't necessarily mean the concentration of acid and base are equal, because if we don't have a 1-to-1 ratio between the two reactants, then we will have different amounts of acid and base, but we will have the same amount of H3O+ and OH- ions. When we look at an acid-base reaction, we frequently use an indicator because it changes colors with pH, and so it lets us easily monitor the pH of the solution based on the color. If you've ever been to a swimming pool or had one at home and done testing on it, you may have seen some similar tests They often get small samples of pool water and do a variety of tests, and then you see color changes. These indicators change color depending on the chemical system in that indicator. And so pH is just one of the many things we can test in that way. We also talk about the pH, and this is a measure of the H3O plus concentration. And so it's useful to help us find out what the concentration is of our unknown species because it allows us to determine the moles of our unknown species. In the next module, we'll talk about oxidation reduction reactions, or redox.